Hello class and welcome back. Today we're going to be running some Charpy impact tests in order to characterize the ductile brittle transition behavior of two materials, A36 steel and 6061 T6 aluminum. This behavior is temperature dependent, so we will be soaking 7 specimens from each material type in liquid baths in order to get them to the temperatures we want. We'll range all the way from 100 degrees Celsius down to minus 75 degrees Celsius. In order to run these tests, we'll be using the Instron Dynatup drop tower here. It's a pretty simple machine. It's got a crosshead that can be driven up and down. Hanging from the crosshead is this tray here that we can stack weights into and control the mass. And below that we have a load cell and a striker, that way we can record the force throughout the tests. Our specimen is supported below in this 3-point fixture, so it's a simple support. We also have a flag here and an optical sensor that will record the velocity at impact. So we have initial velocity, known mass, known drop height. From there we can calculate deflection, impact energy, and other things. All right, we'll go more into this a little bit later on. Here's a close-up of the Charpy specimens. There's the A36 steel, the 6061 aluminum. These are essentially square bars, roughly 8 millimeter by 8 millimeter. Overall length is 55 millimeters, and the notch is midway along the length. The beams will be simply supported at 50 millimeters. That's the span, with the notch facing downward. The notch is 1.2 millimeters deep, and the angle is 45 degrees. So we've got 7 containers here in order to condition our specimens, starting with the hot water all the way down to the very cold acetone. So we have a hot plate here with boiling water. We'll pour some of that into this room temperature water to get it warm. Then we have room temperature ice. We've got water saturated with salt, which lowers the freezing temperature, so we can get that down to about minus 20. And we have some cold acetone and some very cold acetone. We use dry ice to cool those baths. Each of these has a thermocouple temperature sensor in the water, so we're monitoring the temperature in real time. And those thermocouples are attached to a data acquisition system. Take a look at the monitor here. These are the readouts from our thermocouples. So at the left we have our hottest temperature down to the coldest temperature on the right. You can see we have a nice even distribution of temperatures from hot to cold. So here's a closer view of the specimen sitting on the fixture. You can see it's simply supported on the ends, and the notch is facing down. And you can see the striker there, a few millimeters above the specimen, centered over the notch. So we have to establish a zero height position for the setup we have. To do that, we have our specimen in the fixture and the crosshead lowered until the striker is just contacting the specimen. So that's our zero height position. This is also where we will measure our initial velocity. To measure the initial velocity, we have an optical sensor, and I lower the body of that sensor. It reveals this flag here, and you can see there are 2 flags actually with a space between them. When the first flag goes past the optical sensor, it starts counting. When the second flag passes the optical sensor, it stops counting. And the software knows the distance between those flags, so it can then calculate the velocity at that position. And so in order to set that position, I just move the body up, align the bottom with the bottom of the flag, and that sets our flag so that we're going to measure our initial velocity at that point. So after the test, the specimen gets pushed down into this chamber down below, and the carriage stops on these support columns here with the rubber pads, these green pads, and those prevent the carriage from continuing on and crashing into the base of the machine. So any remaining energy left over after our specimen has absorbed its energy is taken up by those columns. So now I'm over at the control PC, Here's our user interface. On the right here, we have our control panel. I can move things up or down. I'm going to move it down to our zero height position. You can see I've already zeroed that. If it wasn't zeroed, I could click that. And we can also weigh our drop mass. So you can see here I have drop point control, and I can choose to drop it from a specified height, or a specified impact velocity, or a specified energy. In our case, we want to drop it from 100 joules. So I can just type that in and say go to energy. And based on the mass, the software can calculate the height that needs to go to. This is basic physics. Energy equals mass times gravity times height. Okay, so there's our drop height. This is the velocity that it's calculating that we'll achieve. And there's our drop weight. So the software has everything it needs to know in order to calculate our energy. Okay, so the aluminum specimens have been soaking for 10 or 15 minutes. They're ready to go. I'm going to go ahead and start testing, but in order to keep track of everything, I've got this worksheet here, and I've got my hot water will be the first one I test. So as I pull the specimen out, I'll record the temperature. I'll test the specimen. I'll record the energy, and then I'll place the broken specimen in that block. And that way we have our specimens correlated with the temperature and energy for all 7. It's just a good way for us to keep track of what's going on here. All right, so I've got some tongs. I'll pull out the aluminum specimen. I'm going to drop it on the table. I'm going to use my gloves. And quickly move over to the machine. Close the door, because I cannot actuate anything with the door open. It's a safety feature. And I'm ready to test. So I'll activate, then drop. And now the crosser will come down to retrieve the hanging mass and bring it back up to the 100 joule energy region. Now I'll use the tongs to go in and retrieve what's left of my specimen. In this case, I have 2 halves. All right. So I'll place those specimens down, record the temperature, and I can record the energy at 17 joules. So there's my worksheet, there are my 2 specimens, and we'll keep these all neatly organized throughout the process. All right, let's move on to the warm water. Our warm water is 47. All right, so we'll do this last aluminum specimen. All right, and record it on my table. All right, I'm going to start from the cold end on the steel specimens, just because my water's not boiled yet. So I'm going to go ahead and load a very cold specimen. Now I can initiate the drop here, and here we go. All right. So there's our first steel specimen, And I'm just going to crank through the rest of these and get them done. Here, you can see the plot that's developed on the screen. We have load deflection curve, load in kilonewtons, deflection in millimeters. The red trace is our load as measured from the load cell. You can see it picks up immediately here upon contact. And then we have a little bit of a plateau here after the peak where the specimen is yielding and then finally fractures and gets pushed down. This green trace is our energy. So the energy is essentially the integral of the load deflection curve. So the area under this curve gives us our energy.
So I've got the 7 steel test specimens lined up here. They're organized from the hottest test temperature here on the left, all the way down to the coldest test temperature here on the right. If you take a look at the fracture surfaces here, we can definitely see some differences here. On the warmer specimens, we have this distorted appearance with these large shear lips on the sides. As we decrease in temperature, the shear lips decrease in size, as does the ductility, until we get all the way down to the coldest specimen where we have a strictly brittle failure, no distortion at all, no contribution from shear. And here's a side view of the 2 extremes. The hottest specimen here with the shear lips clearly visible. You can see how the specimen was torn apart. And then the coldest specimen here, where we had a strictly brittle failure, and the part just snapped. There's no distortion on the edges at all. There are the aluminum specimens lined up after fracture. Again, going from the hottest on the left to the coldest on the right. And if we look at the surfaces, we really can't see any change from the hottest to the coldest. It's a ductile failure all the way along. So we don't have any ductile to brittle transition here with the aluminum specimens. Okay, so these are the final results here. Here are my 2 worksheets. I've got the aluminum here on the left, the steel on the right. Again, we got very little fluctuation in the energy required to break these specimens with the aluminum. It's plus or minus a few joules. With the A36 steel, we go from 91 joules at the hottest temperature down to 8 joules at the coldest temperature. And we can clearly see the brittle to ductile transition. Okay, that's it for this lab. You'll get a set of this data in an Excel spreadsheet. Good luck.